Chapter 2, the first law of thermodynamics. In physical chemistry, system is defined as the part of the universe we wish to study, and the rest of the universe is called the surrounding. A system can be an open system, where matter energy can both exchange with surrounding. For example, if we heat a beaker full of water, energy can go in, the water molecules can go out, and that's an open system. But if we cap it, all right, energy can still go in, but water cannot escape, and that's called a closed system. So closed system, matter does not enter or leave. Now, if the wall of the beaker is insulated, so heat cannot go in, and also capped, so liquid cannot go out, and that's called a closed system. So in a closed system, neither energy nor matter is exchanged between system and the surrounding. Extensive properties are those properties that do not depend on the amount of matter present. These include color, odor, luster, hardness, melting point, boiling point, density, pressure, temperature. Extensive properties are those properties that do depend on the amount of matter present. That include mass, weight, volume, length. And we are going to learn internal energy, Gibbs energy, entropy. These are all extensive properties that will change when you change the amount of substance. Heating is the transfer of energy that makes use of disorderly, apparently random molecular motion in the surrounding. Work is the transfer of energy that makes use of organized motion in the surrounding. Heat and work are two equivalent ways of changing internal energy of a system. Internal energy is the sum of all microscopic forms of energy, includes the kinetic energy, potential energy. Kinetic energy in physics we learn is half mv squared, so it's related to the speed. It relates to motion, and at the microscopic level, it relates to the molecular translation, rotation, vibration, electron translation, and spin, nuclear spin of the molecules. Potential energy is related to the relative position, so it is associated with atomic bonds in the molecule, phase of a system, strong bonds within the nucleus of the atoms itself, energy interaction. All right. So the combination of this kinetic energy, potential energy, give you the total internal energy. So in many cases, internal energy can be absolute value can be complicated, and usually we are not concerned about the absolute value. Instead, we are concerned about the change. It is the internal energy change that is related to how much heat and work that involved in the process. In Chapter 1b, in the kinetic model, one important equation says that the average kinetic energy of a gas molecule is 3/2 kT. So temperature is a measure of average kinetic energy, and this is one molecule in average the kinetic energy. So for 1 mole of molecules, the kinetic energy should multiply by a Avogadro's number, and the K constant combined with Avogadro's number give you the gas constant. So 3/2 RT, that's the average kinetic energy for 1 mole of gas molecules. So at 25 degrees, for example, the molar kinetic energy for gas molecule, all right, you plug in 298 Kelvin, and you will get 3.72 kilojoule per mole. Now, because ideal gas has no intermolecular interaction, if there's no intermolecular interaction, that means potential energy is 0, and therefore, for ideal gas, the internal energy, all right, is only determined by temperature, because there's no potential energy, and so the internal energy is only kinetic energy, which is determined by temperature. All right, and that's a very important conclusion. We'll see. As long as we talk about perfect gas or ideal gas, the internal energy is independent of volume, only depends on temperature. So U is a function of temperature only. The first law of thermodynamics is about energy conservation. It says that energy can neither be created nor destroyed. So if the system internal energy changes, then there must be heat and work involved in the process. The internal energy change should equal to the sum of the heat and the work that are added to the system. And we'll see the equation in the next slide. Here is the equation of first law of thermodynamics. And it says that the delta U, that is the change in internal energy, is accompanied by heat and work. Heat and work are two equivalent ways of changing systems' internal energy. This equation is one of the most important equations in this chapter. And the rest of the chapter is to discuss how to calculate heat, how to calculate work, how to calculate internal energy. Now let's derive an equation to calculate work. In physics, work is defined as force times distance. In chemistry, work, the sign of work is defined as following. Work is positive if the work is done on system by surrounding. Okay, if the work is done by the system to the surrounding, then the work is negative. So remember this: if the system consumes internal energy to do work to the surrounding, and that work is negative. But if surrounding do work to the system to increase internal energy, that work is positive. All right, so this shows a diagram shows a cylinder with gas molecules contained by a movable wall. And so let's assume the gas expand dz. dz is the length. So how much work is involved? So how do you calculate work? Now, according to the equation of physics, work should be force times distance, dz. But what's the sign? Now, in this process, the gas molecules expand, so the work is done by the system. And the gas molecule is the system, all right? So it expands, all right? So because it consumes energy to expand, so the work in this case is negative, and therefore we need to add a negative sign. So d means very small. So if the distance is very small, dz, then the work is also small. So dw equals negative force times distance, dz. Now here you have ex. Ex means external force. So the work is determined actually by the external force. Why is that? Well, imagine the external force is 0. So outside there's no force. Then the cylinder will move freely. You don't need any energy to do work. And therefore you see the work is determined by external force. So it's negative external force times the distance change. In the last slide, we show that if there's a distance change, dz, by the gas molecules, the work is negative force times distance change. Now this equation is not very useful because when we discuss gas phase, we use pressure, we use volume, we seldom think about distance change, force. All right, we need to use pressure and volume. So we need to make some modifications to this equation. Now, first we realize force is related to pressure by area. So area times pressure equals force. So plug into this equation and we get this equation. dW equals negative external pressure times area times distance. And if we look at this diagram, the area times distance, that's just the volume change. So that's the dV. All right, and then plug in, so combine this together becomes dV. So now you have a very useful equation. dW equals negative external pressure times volume change. So if we know volume change by expansion, we know external pressure, then we can calculate work, and that's an important equation. In the last slide, we show that if gas molecules expand a very tiny volume change dV, the work is done negative external pressure times this small volume change. What if the volume change is not very small? Okay, if it's changed from initial VI to final. So here is the volume change. So how do you calculate work? Okay, to do that, we can separate this process into many small volume changes. Okay, so dV1 is the small volume change which has a external pressure corresponding to this volume change, and for dV2 there's another external pressure corresponding to this one. So many small segments, and there's the total work during this process is the sum of the work of each of these small segment. All right, so it's negative P1 times dV1, P2 times dV2. This is the work for each of the segments. So you add it together. Now in calculus, the sum of all these small segments is called integration. So if the volume change is measurable change, okay, not infinitesimal small, then we should use integration from initial volume to the final volume, external pressure times volume change, dV. Don't forget there's a negative sign. Since the calculation of work involves some knowledge of calculus, I want to have 3 slides to go over the concept of derivative and integration. Now, derivative is a measure of rate change, and integration is a measure of total function change. Derivative measures instantaneous velocity. Calculation of total function change can only be achieved by integration. Integration is related to the area below a certain function. Now let's calculate an area of a rectangle. So you have a function fx equals 10. It's a flat line, and that's a constant. And the x change from A to B. And this encloses a rectangle. And the area can be easily calculated by the length b minus a and the width, which is 10. So 10 times b minus a, that's the area below this constant function, fx equals 10. Now, how do you calculate the area below this function, which is not a constant, fx? So to calculate the area below this function, we separate into many small rectangles. Each rectangle can be calculated by fx times delta x, fx2 times delta x. So you add all together, and this is defined as integration. So fx dx integration from a to b, and that's the area below this function. Okay, so to calculate integration, we have 2 ways to do it, and we'll see in the next slide. Here shows 2 examples of integration. So first, integrate function 2 dx from 1 to 2. Now, one way to do it, to use a common integral and then combine with the fundamental theorem of calculus. So 2 is a constant. So a constant dx integration gives you kx. Kx dx equals kx. So here, 2 dx should give you 2x. All right, so that's the integral. Now from fundamental theorem, it says it should be final minus initial, and so it is from 1 to 2, and according to fundamental theorem, it should be 2 times final is 2 minus 2 times initial 1, and that gives you 4 minus 2 is 2. All right, so that's method 1, and the answer is 2. Now method 2, we use the definition. Integration is the area below the function. So the function here is 2, fx equals 2. So this is fx equals 2. And x change from 1 to 2. And so we're asking to calculate the area of this rectangle. And so the length is 2 minus 1 is 1. So this is 1. And the width is 2. So 2 times 1, the area equals 2 times 1 is 2. And that gives you the same answer. Okay. Now let's look at the second one. X dx integration from 1 to 2. So we look at the common integral. We have xn dx equals 1 divided by n plus 1 times xn plus 1. In this case, the n is 1. And therefore, according to this equation, should be 1 divided by 1 plus 1 x1 plus 1. And that is half x to the second power. So the integration of this one is half x squared. And it changed x from 1 to 2. So according to the fundamental theorem, it should be final 2 the squared minus initial 1 squared. And 2 squared is 4. 4 divided by 2 is 2. So 2 minus half. That gives you 3 over 2. Okay, so that's method 1. Now method 2, again, we look at the area of the function. So the function is x. So fx equals x, and that's a straight line. So fx equals x. And the change is from 1 to 2. So 1, 2. And because fx equals x, so when x equals 1, y must be also 1. When x equals 2, y also be 2. And how do you calculate the area below this function? Okay, so we are calculating the area here. Okay, now you notice that this area is a big triangle minus a small triangle, the area. So area is the area 2, which is the triangle, large triangle, minus the small triangle. The large triangle is half length, which is 2, times the height is 2. The small triangle length is 1, height is also 1. Okay, and so you get 2 minus 1.5. Again, give you 3 over 2, so you get the same answer. So both methods give you the same answer for integration. Let's now come back to the equation to calculate work. So if volume change is very small, infinitesimal small dV, the work is calculated by negative external pressure times volume change. But if volume change is measurable from initial to the final, then we have to integrate. Okay, we should separate into many segments, add together, and that's called integration. So negative integration from external pressure dV from V1 to V2. To calculate this integration, we have to know how external pressure change as a function of volume. And in the next few slides, we're going to see some special cases where we can calculate work. The first special case we are looking at is constant external pressure. So this pressure is a constant, and it changes volume from V1 to V2. And the pressure here is constant. The work is calculated by integration, which is the area under this constant pressure. And so area can be easily calculated by external pressure times volume change. Of course, to calculate work, you have a negative sign in front of it. Of course, we can also use this equation, and because this is a constant, you move out of the integration, so that gives you negative external pressure times integration of 1 dV, and 1 dV integration is just volume, V final minus E initial, and that again give you the equation negative external pressure times volume change. So this is a very simple equation, and if pressure is a constant, then work is just negative pressure times volume change. And although this is very simple, this is a very important equation because many processes are constant pressure process. For example, biological process happens in our body is constant pressure 1 atmosphere. So you must remember this very important equation. The second special case we're looking at is called a free expansion. Free expansion means outside pressure, external pressure is 0. So gas expand against 0 pressure. And you can think about this as a special case for constant pressure process. And so because outside pressure is always 0, so work must also be 0. No work is done when a system expands freely. The third special case we are looking at is called a reversible expansion. So let's look at what is reversible expansion. So here shows a cylinder with gas confined by a movable wall, and we have objects that exert a pressure. So when they are at equilibrium, then the pressure inside a gas should equal to the external pressure outside. Okay, so these two pressures are the same. Now, when the gas, if the gas expands to a larger volume, all right, and volume increase, pressure must decrease. So P2 becomes smaller. And now if you cut the objects away so that the external pressure also reduced and equal to the P2. Okay, so you maintain outside pressure equals inside pressure. And if you maintain in the whole process, okay, at any instant, inside pressure always equals to the outside, even though it's expand. All right, every step you maintain these two pressure the same, then this process called reversible expansion. And so at any instant, these two outside equals inside. If you add a infinitesimal amount of pressure inside, it will expand. If you add this infinitesimal amount of pressure outside, then it will compress. So any step, it can expand or compress. It's reversible, and therefore that's why it's called a reversible expansion. So a reversible change in thermodynamics is a change that can be reversed by an infinitesimal modification of a variable. And for expansion, reversibility can be achieved by gradually changing the weight until final pressure is achieved. In the process, this is maintained so that at any instant, inside pressure always equals to outside pressure. This is the condition for the reversible expansion. Now please note that this doesn't mean these are constant. They actually change. So imagine when you expand, this pressure will become smaller, but the outside pressure also becomes smaller. So at any instant, they always maintain the same, and that's called a reversible expansion. Let's calculate work for a reversible process. We start with the general equation. W equals negative integration external pressure times volume change from V1 to V2. So here is the initial volume, all right, and then expand to the final volume. And because it's reversible, that means the external pressure always equal to the pressure inside, the gas pressure. Okay, so let's look at this equation. All right, now usually external pressure has nothing to do with the volume, because the volume is the gas volume, but the pressure is outside, so they have no relation. However, if it's reversible, that means at any instant, external pressure equals the pressure of the gas. And so this equation we can change to the pressure of the gas. And the pressure of the gas, pressure of the volume, they are related by ideal gas law. So only when it's reversible, now external pressure becomes the pressure of the gas using ideal gas law. So we have this equation, negative integration nRT divided by V times dV. So this V is the volume of the gas. So we have a possibility to integrate this, but in order to integrate this equation, we still need to know the temperature. Assume temperature is constant. So if this is constant, R constant, N constant, we can move all out of the integration. And so now you have negative nRT integration dV over V. Okay, so we know that 1 over x dx is ln x, and therefore this will be ln V. Now it changed from V initial to V final, so according to the fundamental theorem, should be final minus initial. And in mathematics, this can be written as ln V final divided by initial. And therefore, we have this important equation for isothermal reversible expansion. The work is negative nRT ln V final divided by initial. Remember, this equation is only valid if it's reversible when the external pressure equals the pressure of the gas and constant temperature isothermal process. Okay, so if it's isothermal, and the plot is Boyle's law, so that's the isotherm, and the work is under this curve, so that's the area. So that's the negative nRT ln V final divided by initial. Let's summarize how to calculate work. In general, if the volume change is infinitesimal small, the W equals negative external pressure times volume change. But if volume change measurably, we use integration, negative integration PEX, external pressure times volume change. So we learned some special cases. One is the volume is constant. Well, actually, we didn't say what, but if volume is constant, you look at this equation, and that means delta V is always 0, and so work is 0. So as long as volume is constant, work always 0. But if pressure is constant, okay, that's the first case we looked at. Pressure is constant, then the integration becomes simple. This move out, so it's just negative external pressure times volume change. Okay, so delta V is the final minus initial. Remember, this is a simple equation, but very important. Constant pressure. All right. For free expansion, work is always 0. And if it's reversible and a constant temperature, the work is calculated by negative nRT ln V2 divided by V1, or final over initial. Now, if we don't have volume, what can we do? Well, because temperature is constant, it obeys Boyle's law, so P1 V1 equals P2 V2, and therefore V2 over V1 should equals to P1 divided by P2, and so this equation can also be written as negative nRT ln P1 divided by P2. Okay, because V2 over V1 equals P1 over P2. Now, if you want to write as final over initial, all right, P2 over P1, then you have to change sign to positive. All right, so positive nRT ln P2 over P1. Okay, so these are the equations to calculate work for special cases, and as long as you can remember all these equations, you are fine. And it's important that to use each of equation, you must know the condition. All right. So, for example, this is only valid for constant pressure. All right, and this is only valid for reversible constant temperature. Here is a sample question about calculating work. So what we know is gas phase initially has pressure 8 atmosphere, volume 1 liter, temperature 298 Kelvin, number of moles 0.327 moles. So we know everything about the initial state. Now we also know after expansion, pressure becomes 2, volume becomes 4. So the volume increase, pressure decrease. Number of moles doesn't change, temperature doesn't change. So we know the final state. So we know initial state, we know final state. The question is how much work is involved in this process? Can we calculate work? So if we look at the last slides, the list of equations, okay, every equation needs a condition. So for example, is this a constant pressure? We don't know. It didn't say outside pressure is constant. Is it free expansion? No, it didn't say that. It is isothermal reversible. Well, even if its temperature is constant, it doesn't say it's reversible. So we don't know anything about outside pressure. And therefore, we cannot use any of the equation to calculate this. In order to calculate work, we have to know the path, all right? And suppose now we have more information. Suppose outside pressure is 0 from initial state goes to this final state. Then because in a free expansion means outside pressure is 0, work is 0. Now, if the process is constant external pressure, outside pressure is 2 atmosphere. Note that the 2 atmosphere is the final pressure of the gas. So initially the gas has 8 atmosphere. Outside pressure is 2. So the gas will expand until it becomes pressure 2 equals the outside pressure. It stops, and that is fine. And because it's constant external pressure, if you look back to the last slides, we know the work can be calculated by simply negative pressure times volume change. Note that this equation is only suitable for constant external pressure. So negative 2 atmosphere times volume change is 4. Okay, that's the final minus initial, 4 minus 1. All right. Note the unit is atmosphere and liter, and you need to convert this to joule. So the final answer is negative 607.9 joule. Okay. Now you can how do you do that? Your liter you can change to cubic meter, atmosphere change to Pascal, and so everything is SI unit. That will give you a joule. Now, if the process is isothermal reversible, okay, so temperature is constant, but outside pressure initially equals to 8, and then becomes smaller and smaller until 2, always equal to the inside pressure, and that's a reversible. So isothermal reversible process. And then the equation to calculate the work, all right, is this: negative nRT ln V2 over V1. Okay, plug in the data, and you will get negative 1,124 joule. Okay, pay attention to the unit. All right, so that's a reversible process. So this problem tells us several things. First thing is, now even though we know the initial state, we know the final state, we still cannot calculate work. Okay, work is not a state function. State function. Okay, what kind of functions are state function? We will learn later. Internal energy, Gibbs energy, those are state function. As long as we know initial state, final state, we can calculate delta G, delta U. But work is not. Work depends on path. Okay, we need to know if this is constant pressure, or the process is constant volume, or isothermal reversible. So we have to know the path to calculate work. Okay, that's one important thing we need to remember to calculate work. Second thing we notice that among all these processes, isothermal, reversible, the work is negative 1124, much larger than constant pressure and free expansion. In fact, you can see the constant pressure work is under this area. So this is the pressure. So this area is the work for constant pressure. But reversible isothermal is under this isotherm. So this is the area, and that's much larger. Okay, so that's the maximum work. So reversible work is the maximum work that can be done by a gas. Here is another sample question to calculate work. A system containing 2.5 moles of ideal gas is taken through the cycles indicated below. All right, and therefore we need to be able to read this diagram and see what this means. It asks you to calculate work for each segment for the cycle. So from 1 to 2, okay, as you see, the pressure doesn't change because this is pressure. So a horizontal line means pressure doesn't change. And therefore, the first step is constant pressure, all right? And the second process, from 2 to 3, is vertical. And this is a volume. So a vertical line means volume doesn't change. And so it's a constant volume. And the third process, from 3 to 1, and that looks like isotherm. And so it's constant temperature. Okay? So with this information, now we can calculate the work, because for constant pressure, the equation is negative pressure times volume change. Okay, so simply pressure, external pressure times volume change. And the pressure is given 16.6 bar, volume is 25 minus 1. Okay, of course you need to change to SI unit to get joule. So that's the first step. Second step, constant volume. What is the work? All right. If you don't remember, go back to the slides. You will see when volume is constant, work is always 0. Okay, no work is done. And the third one, constant temperature, isotherm, is not enough. You have to know whether it's reversible or not. So in order to calculate work, all right, we have to assume this is reversible. Constant temperature, reversible. For that process, the equation is negative nRT ln V2 over V1. So usually we say final over initial. Final over initial. So for this process, final is state 1, initial is state 3. So V3 or V1 divided by V3. Okay, and V1 is given 1 liter. V3, remember, it's constant volume, so V3 equals V2, which is 25. All right, and that gives you 5.35 kilojoule per work. So this question, you need to be familiar with this diagram to know which process is constant pressure, constant volume, and isothermal process to calculate work. So far in this section, we have derived equations to calculate work. And the next few slides, we briefly introduce heat and internal energy. So heat is the energy that flows due to temperature difference. Now heat is not a property of a gas. You cannot say a gas contains how much heat. It is a transitive property. So you can say during this process, how much heat is transferred. In chemistry, the sign of heat is defined similar to work. So if heat is deposited to the system from surrounding, and that heat will increase internal energy, and that heat is positive. Okay, just like work. If work is done on the system by the surrounding, to increase internal energy, that is positive work. So if heat is withdrawn from the system to the surrounding, for example, a reaction is exothermic, release heat to the surrounding, that heat is negative. Okay? Just like work, as we see in the examples, work is path dependent, not a state function. Same thing is Q. Heat depends on path. All right. Here is the first law, delta U equals Q plus W. We have seen from the last few slides that both Q and W are path dependent. However, when you add these two together, we get delta U, which is a state function that is path independent. For example, if we go from state 1 to state 2, okay, this is state 1, this is state 2, but we choose different paths. For example, path A, B, and C. Then the work done in path A, path B, path C will all be different, and the heat involved in A, B, C are all different. But the delta U between state 1 and state 2 are the same, no matter how you go from initial state to final state. All right, choose different path, they get the same delta U. So delta U only depends on the state, initial state, final state, not the path. Okay, so U is a state function whose value is independent of the path. We use capital letter U to represent the state function, but lowercase q and w to represent non-state function. Here are two sample questions about delta U. A sample of gas changes in volume from V1 4 liter to V2, okay, 6 liter, against the external pressure 1.5 atmosphere. So that indicates it's a constant external pressure, and simultaneously absorb 1000 joule. So that's the Q. So the question is, what is the change in internal energy of the system, delta U? Okay, so in this question, it gives you pressure, volume, and heat to calculate delta U. Okay, to calculate delta U, we can use the first law. So first law, delta U equals Q plus W, and Q here is 1000 joule. Is it positive, negative? Because it absorbs heat. Heat goes to the system to increase internal energy. So this is a positive. All right. Now what about W? Now W in this process is a constant external pressure. So the work can be calculated by negative pressure times volume change. Okay. So then add these two. So you calculate the work, which is negative pressure times volume change. All right, and you need to change atmosphere to Pascal, liter to cubic meter, you get joule. All right, and Q is positive 1000, and add together give you 696 joule. In sample question 2, a 1 liter sample of gas, so that's volume, and pressure is 1 atmosphere, temperature 298 Kelvin, expand isothermally, reversibly to 10 liter. So if this is state 1, it goes to state 2, volume 2. It is then heated to 500 Kelvin, so that's the state 3, and then compressed to 1 liter, so that's the 4. All right, and that's volume 4, and then cooled to temperature T, 25 degree. So what is delta U? So this question looks very complicated, but if you look at the final state, which is 1 liter, that's the same as initial, 1 liter, 1 liter. And the temperature 25 degree is 298 Kelvin, so the temperature is the same as initial state. Volume is the same as the initial state. The number of moles shouldn't change. So same number of moles, volume, temperature the same, and therefore you go back to the initial state. So if you draw the diagram, so this is initial state. Okay, so it go to different state, and then finally you go back. So what is delta U? All right. Now, because the internal energy is a state function, so no matter how many steps you go, as long as you go back to the initial state, it doesn't change state because you go back to it, and so delta U will be 0. Okay.